Picture a time before stars, before galaxies, before even light had fully broken free from the darkness. The early universe was a place of unimaginable extremes, where the laws of physics, as we know them, were still taking shape. It's a realm so alien, so profoundly mysterious, that even our most advanced telescopes can only catch faint whispers of its secrets. Yet those whispers tell a story that defies everything we thought we understood about space and time. What if I told you that some of the greatest cosmic puzzles aren't lurking in the distant reaches of space today, but are hidden in the universe's first fleeting moments? We're talking about phenomena so bizarre they challenge the very foundations of science, missing mountains of antimatter, invisible forces twisting the fabric of reality, and perhaps even echoes of universes that existed before our own. These aren't just abstract ideas, they're clues to a past so strange it reshapes how we see our place in the cosmos. That's exactly what we're diving into today, 30 of the most jaw-dropping, mind-bending mysteries from the dawn of existence. From the cosmic dawn's first glow to the shadowy enigmas of dark matter's birth, we'll unravel the questions that keep astronomers awake at night. And here's the thrilling part. Every mystery we uncover doesn't just reveal secrets about the past, it rewrites what's possible for the future. So buckle up, we're about to journey back to the very edge of time itself, where the universe was young, wild, and full of surprises we're only beginning to comprehend. Hidden in the fog of the early cosmos lies one of the greatest unsolved puzzles, the birth of the very first stars. Astronomers call them population 3 stars, celestial giants that lit up the darkness long before galaxies like our Milky Way even existed. Unlike the stars we see today, packed with metals and complex elements, these pioneers were made of nothing but hydrogen and helium, the raw ingredients left over from the Big Bang itself. They should have been impossibly bright, hundreds of times more massive than our Sun, burning furiously and dying young in spectacular supernovas. Yet despite decades of searching, we've never spotted a single one. Why? Because they vanished billions of years ago, and their light is so faint and stretched by the expansion of the universe that even our most powerful telescopes struggle to catch even a ghostly imprint. But finding them matters more than you might think. These stars were the universe's first factories, forging heavier elements in their cores and scattering them across space in their explosive deaths, elements that would later form planets, oceans, and even life itself. Without them, the cosmos as we know it wouldn't exist. The hunt continues with next-generation observatories like the James Webb Space Telescope, peeling back the layers of time to glimpse that elusive cosmic dawn. If we succeed, it won't just solve a mystery, it'll rewrite the story of how everything came to be. Imagine flipping the cosmic light switch, taking a universe shrouded in thick hydrogen fog and suddenly making it crystal clear. That's exactly what happened during the mysterious epoch of reionization, a pivotal chapter when the first starlight and galaxies ripped apart the neutral hydrogen gas that had blanketed space since the Big Bang. But here's the twist. This transformation didn't unfold in the slow, gradual way scientists expected. Instead, the universe went from opaque to transparent in what amounts to a cosmic blink of an eye, and we still don't fully know how. For hundreds of millions of years after the Big Bang, the cosmos was a soupy haze of hydrogen atoms, absorbing light like a cosmic fog. Then something, or some things, began blasting out enough ultraviolet radiation to tear those atoms apart, stripping away their electrons in a process called ionization. The leading suspect, those first generations of massive stars and voracious black holes in early galaxies. But when astronomers crunch the numbers, there's a glaring mismatch. There simply aren't enough of these ultraviolet powerhouses in the early universe to account for how quickly reionization occurred. It's like trying to explain how a single flashlight lit up an entire football stadium in seconds. Even stranger, pockets of the universe seem to have cleared at different rates, as if some cosmic landscaper was flicking switches at random. Some regions became transparent while others remained shrouded, creating a patchwork of light and shadow across the young cosmos. This unevenness hints at forces we're only beginning to map, perhaps undiscovered populations of dwarf galaxies too faint to detect, or exotic processes like dark matter decay adding energy to the mix. The stakes couldn't be higher. Without reionization, light would still be trapped today, and telescopes like Hubble and Webb would stare into nothingness. Solving this puzzle isn't just about filling in a textbook. It's about uncovering whether we've missed entire categories of celestial objects or fundamental physics that shaped the universe's most transformative era. Every new observation peels back another layer, bringing us closer to understanding how darkness gave way to the radiant cosmos we call home. Standing on the shoulders of the modern cosmos, it's staggering to realize we might be alone. The universe has had billions of years and trillions of galaxies to spawn intelligent life, so why does the cosmic dial seem stuck on silence? This is Fermi's paradox in its rawest form, and when we reframe it against the early universe, the mystery only deepens. The numbers alone should overwhelm us. By the time our solar system formed, the universe was already over 9 billion years old, ample time for civilizations to rise, expand, and leave their mark across galaxies. Yet when we peer back through time, scanning the chemical fingerprints of ancient stars or the radio whispers from primordial space, we find nothing. No megastructures, no interstellar probes, no galactic empires. Just an eerie stillness stretching back to the cosmic dawn. Some scientists argue the answer lies in what's called the Great Filter, a hypothetical barrier that prevents life from progressing to interstellar scales. It could lurk in our past. Perhaps the leap from simple chemistry to complex life is astronomically rare, making us cosmic lottery winners. Or worse, it might wait in our future, some inevitable catastrophe that dooms all advanced civilizations before they can spread. But the early universe adds haunting layers to this puzzle. Imagine civilizations born in those first eras of star formation, gifted with billions of extra years to evolve. If they existed, why didn't they reshape the cosmos in ways we'd notice? Could dark matter or early physics have stifled their rise, or does intelligence inevitably lead to self-destruction, leaving the universe perpetually resetting to silence? One provocative theory suggests we're simply too early, that the golden age for civilizations lies far in the future, when stars burn slower and energy is easier to harness. Or perhaps the answer is darker, that the universe, for all its grandeur, is fundamentally sterile and we're the fluke. Every silent galaxy we observe tightens the knot of this paradox, urging us to confront whether we're pioneers, survivors, or something far lonelier. The deeper we probe, the more Fermi's question morphs from curiosity to existential mirror. Solving it won't just tell us about aliens, it'll reveal whether humanity's story ends with a whisper or a symphony written across the stars. Dark matter doesn't just hide in the shadows, it built them. This invisible ghost of gravity makes up 85% of the universe's mass, yet it refuses to interact with light, with matter, with anything except through its gravitational pull. And when we trace its fingerprints back to the cosmic dawn, the plot thickens impossibly further. Take the earliest galaxies. According to our best simulations, these fragile structures should have taken billions of years to coalesce under ordinary gravity alone. Instead, they formed at breakneck speed, as if some unseen scaffold were holding them together. That scaffolding, dark matter's gravitational web, which must have already existed in vast, intricate networks when the universe was barely a toddler. But here's the catch: the patterns we observe in ancient galactic clusters don't quite match what our models predict. Some primordial galaxies are clumped too densely, others spread too thin, as if dark matter wasn't distributed smoothly after the Big Bang, but instead pooled in mysterious cosmic puddles we can't yet explain. The enigmas multiply when we examine individual galaxies. Modern ones rotate so fast they should fling stars into the void. yet something invisible grips them tightly, presumably a halo of dark matter. But early galaxies show even more bizarre behavior. Some appear to have formed stars too efficiently, as if dark matter's grip was stronger back then. Others lack the expected dark matter entirely, raising the terrifying possibility that this substance isn't just passive scaffolding. It might evolve, decay, or interact in ways that defy the rules we've written for it. What truly rattles scientists is the timing. Dark matter seems to have shaped galaxies before normal matter even had a chance to catch up, like an architect building a city before the bricks were invented. This challenges the standard story of cosmic evolution, where both types of matter should have danced together from the beginning. Some theorists now speculate that dark matter might have experienced its own dark Big Bang, a separate explosive birth that gave it a head start. Others wonder if it's not one substance but many different flavors with unique behaviors that sculpted the early universe in ways we're only beginning to glimpse. Every telescope pointed at the cosmic dawn brings new contradictions. The Euclid space mission, designed to map dark matter's distribution, recently found filaments of the stuff connecting galaxies more tightly than anyone predicted. Meanwhile, studies of the cosmic microwave background, the afterglow of the Big Bang, reveal tiny temperature fluctuations that suggest dark matter might have interacted with itself in the universe's first seconds, leaving scars we can still read today. The deeper we dig, the clearer it becomes. Dark matter isn't just a missing piece of the puzzle. It's the shadowy hand that assembled the puzzle in the first place, and until we understand its origins, we're staring at a picture with 85% of the pieces still blank. Dark energy shouldn't have been in a hurry. For decades, scientists assumed this mysterious force responsible for the universe's accelerating expansion only took center stage in the last few billion years, after gravity had its chance to weave galaxies and clusters together. But when astronomers recently peered back to the universe's first billion years, they stumbled on something unsettling: signs that dark energy might have been flexing its muscles far earlier than anyone predicted. The evidence comes from ghostly imprints in ancient light. By studying the clustering of early galaxies in data from observatories like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope, researchers noticed something off. The distribution of these primordial structures doesn't quite match what standard models predict. Instead of gravity smoothly sculpting matter into predictable patterns, there are strange gaps and unexpected voids, as if an invisible hand was already pushing space apart while the cosmos was still in its infancy. This raises a startling possibility. Dark energy might not be constant, as Einstein once theorized, but dynamic. Imagine a cosmic dimmer switch where this repulsive force's strength has changed over time. Early on, it could have pulsed weakly, subtly influencing the universe's expansion before fading into the background, only to resurge violently billions of years later. Alternatively, there might be multiple forms of dark energy, each dominating different cosmic epochs, like actors taking turns on a stage. What makes this especially puzzling is the timing. During the universe's first billion years, matter was still dense enough that gravity should have overwhelmed any repulsive force. For dark energy to leave fingerprints so early, it would need properties that defy our current understanding, perhaps interacting with dark matter in ways we haven't yet imagined, or tied to exotic particles that vanished as the cosmos cooled. The implications are profound. If dark energy was active during the cosmic dawn, it could explain lingering mysteries, like why some early galaxies formed with bizarre shapes, or why certain regions of space emptied out faster than expected. But it also forces us to confront an uncomfortable truth. Our best model of the universe, the lambda-cold dark matter framework, might be missing a crucial chapter. Upcoming telescopes like the Vera C. Rubin Observatory aim to settle the debate by mapping millions of ancient galaxies with unprecedented precision. Each new dataset brings us closer to answering whether dark energy's early appearance was a fluke, or the first clue in rewriting cosmic history. One thing's certain, the universe's greatest enigma just got a lot more complicated. Black holes aren't just cosmic vacuum cleaners, they might be cosmic pioneers. While we typically think of them as the corpses of massive stars, there's a tantalizing possibility that some black holes existed before stars ever ignited. These primordial black holes, if real, would have formed in the chaos of the early universe mere moments after the Big Bang, when space was so dense that pockets of matter could collapse under their own weight without needing a star's death to trigger them. This idea flips our timeline of cosmic evolution upside down. Instead of stars lighting up first and then seeding the universe with black holes, these ancient gravitational traps could have been the scaffolding around which the first galaxies coalesced. Imagine a universe where black holes weren't the end result of stellar life, but the starting points for cosmic structure itself. The evidence is still circumstantial, but the clues are piling up. Some ultra-distant quasars, extremely bright objects powered by supermassive black holes, appear too early in the universe's history to have formed through conventional means. According to standard models, these behemoths should have needed billions of years to grow by swallowing gas and merging with other black holes. Yet there they are, blazing away when the universe was less than 1 billion years old, as if they were already fully grown. Primordial black holes could solve this riddle by giving these giants a head start, seeding the cosmos with ready-made gravitational anchors, but the wildest twist comes from dark matter. Some theorists suggest primordial black holes could account for part, or even all of this invisible substance. After all, if enough of them formed in the early universe and then drifted silently through space, barely interacting with anything except through gravity, they'd match dark matter's elusive profile perfectly. It's an elegant solution, but there's a catch. Primordial black holes would leave subtle fingerprints, like distorting the light of distant stars or triggering gravitational waves when they collide. So far, searches for these signals have come up empty, tightening the constraints on how many could realistically exist. Yet the mystery deepens when we consider their potential sizes. Primordial black holes could range from the mass of a small asteroid to thousands of suns, each born from quantum fluctuations in the infant cosmos. The smaller ones would have evaporated by now, thanks to Hawking radiation, possibly leaving behind explosive bursts of energy we've yet to detect. The larger ones might still lurk in galactic halos, invisible but for their gravitational pull. What's truly mind-bending is the implication for cosmic history. If these black holes were widespread, they could have jump-started the formation of the first stars and galaxies by pulling matter into dense knots, creating hotspots where gravity did the heavy lifting long before nuclear fusion took over. They might even explain some of the universe's odd symmetries, like why certain large-scale structures appear more clustered than our models predict. The hunt for these cosmic relics is heating up. New telescopes capable of spotting gravitational lensing events, brief flashes caused by invisible objects passing in front of stars, could finally settle the debate. Meanwhile, physicists are re-examining the conditions of the early universe, testing whether the right mix of turbulence and density could have spawned black holes straight from the primordial soup. One thing's certain, if primordial black holes are real, they're not just footnotes in cosmic history. They're the unseen architects of everything that followed, rewriting the story of how darkness gave birth to light. The James Webb Space Telescope was supposed to clarify the cosmic dawn, not throw it into chaos. Yet that's exactly what happened when it spotted galaxies so massive, so mature, they had no business existing when the universe was barely a toddler. These cosmic anomalies, some over 100 billion times the mass of our Sun, appear fully formed in Webb's infrared gaze when the cosmos was less than 500 million years old. According to every mainstream model of galaxy formation, that's simply impossible. Structures that colossal should have taken billions of years to assemble through gradual mergers and star formation. Instead, we're staring at galactic titans that seem to have sprung into existence overnight. Take one infamous example, Glass Z13, a galaxy so ancient its light has traveled for over 13 billion years to reach us. Despite its extreme youth in cosmic terms, it already contains multiple generations of stars and a well-defined structure, something that should require at least 1 billion years to develop. Even more baffling is that Webb found dozens of similar galaxies, ruling out a fluke. It's as if we dug up a fossil of a modern oak tree in a geological layer reserved for single-celled organisms. Theories are scrambling to catch up. One radical idea suggests these galaxies formed around supermassive primordial black holes, whose intense gravity accelerated star formation at unprecedented rates. Others propose that the early universe's denser environment allowed gas to collapse directly into massive structures without the slow, hierarchical growth we observe later. Some even entertain the notion that dark matter behaved differently back then, clumping faster and providing a hidden framework for rapid galaxy assembly. But the most unsettling possibility that we've misunderstood time itself. Cosmologists rely on redshift, the stretching of light's wavelength as space expands, to measure cosmic distances and ages. What if unknown physics in the early universe altered how light traveled, making these galaxies appear older and farther away than they truly are? It's a long shot, but when faced with the impossible, every hypothesis deserves scrutiny. Webb's discoveries have turned a quiet corner of astrophysics into a battleground. On one side, traditionalists argue our simulations must be missing key physics, like turbulent gas dynamics or extreme star formation efficiencies. On the other, iconoclasts whisper about rewriting fundamental laws. The truth might lie in between, a reminder that the universe has never been obligated to conform to our expectations. Every new Webb image peels back another layer of this mystery, revealing galaxies with intricate spiral arms, massive bulges, and even signs of early supermassive black holes, all where there should be only shapeless infant blobs of stars. These aren't just outliers, they're clues that the cosmic dawn was wilder, more inventive, and far less predictable than we ever dreamed, and that realization changes everything. If galaxies could form this rapidly, what else did we get wrong about the universe's first chapters? The answer might not just reshape our past, it could redefine the future of cosmology itself. Think of the universe's ledger, a cosmic balance sheet where every atom should theoretically be accounted for. But when scientists tally up all the ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us, they come up short. Roughly half of it has gone missing. This isn't some exotic dark matter puzzle. We're talking about the very stuff we're made of, the baryonic matter that should be lighting up telescopes or casting shadows across space. And its disappearance is one of the most embarrassing gaps in modern cosmology. The math is straightforward. By studying the cosmic microwave background, the afterglow of the Big Bang, we can calculate how much ordinary matter the universe was born with. When we add up everything we've detected since stars, galaxies, gas clouds, the numbers don't come close. It's like pouring water into a glass and watching half of it vanish before your eyes. Where did it go? The leading suspect is the diffuse web of gas strung between galaxies, known as the warm-hot intergalactic medium, or WIM. This isn't the dense, glowing plasma we see in nebulae. It's a sparse, superheated soup of particles, so wispy it's nearly invisible. Picture steam rising from a sidewalk after rain, barely there but real. Theorists argue this WIM could hide the missing baryons, woven into vast cosmic filaments that thread the universe like an invisible spiderweb. The challenge: detecting something so faint it barely interacts with light. Innovative techniques are cracking the case. Astronomers hunt for subtle distortions in the light of distant quasars as it passes through these filaments, like tracking a flashlight beam through fog. Others look for faint X-ray glows emitted when the gas is heated to millions of degrees by collapsing galaxy clusters. Recent breakthroughs suggest we're finally spotting whispers of this hidden matter, but the signals are so weak they're drowned out by cosmic noise. The stakes are higher than just balancing the books. If the missing baryons are trapped in these filaments, they're not lost, just transformed. They could be the fuel for future galaxies, the raw material for generations of stars yet unborn. Or they might hold clues to why certain regions of the universe evolved faster than others, seeded by uneven distributions of this elusive matter, yet some scientists whisper of darker possibilities. Could a fraction of these baryons have decayed into unknown particles, or been swallowed by some early cosmic process we haven't even imagined? Every undetected atom is a silent challenge to our understanding of how the universe organizes itself. The answer won't just solve a numerical discrepancy, it'll rewrite the story of where we come from and what the cosmos is truly made of. If there was ever a cosmic accounting error, the lithium discrepancy would top the list. According to our most precise models of the Big Bang's first minutes, a process called Big Bang nucleosynthesis, 3 key elements should have formed in abundance: hydrogen, helium, and lithium. Hydrogen and helium check out perfectly, matching predictions down to the decimal. But lithium, the universe seems to have misplaced 2/3 of its expected supply, and this shortage has haunted cosmologists for decades. The math is airtight. In the searing heat of the early cosmos, just minutes after the Big Bang, protons and neutrons fused to create these primordial elements. The equations say there should be about 1 lithium atom for every 10 billion hydrogen atoms in ancient stars, the relics of that era. Yet when astronomers measure the oldest stars in our galaxy, ones that formed from nearly pure Big Bang material, the lithium levels are stubbornly 3 times lower than expected. It's as if someone scrubbed the universe's birth certificate clean of this crucial detail. So where did it go? One leading theory points to stellar culprits. These ancient stars might have processed lithium like cosmic furnaces, burning it up in their cores or dredging it down to layers we can't observe. But here's the catch: even the most meticulous stellar models can't account for such a dramatic shortfall. Some stars do destroy lithium, but not enough to explain the gap, and others actually produce it, making the mystery even deeper. Then there's the more radical possibility. Our understanding of nuclear physics in the early universe is incomplete. Could unknown particles or forces have interfered with lithium's formation? Actions, hypothetical lightweight particles, have been proposed as potential saboteurs, subtly altering nuclear reaction rates in ways we haven't accounted for. Others suggest that the density of neutrons during nucleosynthesis wasn't as uniform as we assumed, creating pockets where lithium couldn't form efficiently. But the most tantalizing and unsettling solution involves dark matter. Certain exotic dark matter particles might have collided with atomic nuclei in the early universe, disrupting the delicate dance of protons and neutrons that birthed lithium. If true, this wouldn't just solve the lithium problem. It'd be the first direct clue that dark matter interacts with ordinary matter in ways beyond gravity. The hunt for answers has turned into a cosmic detective story. Laboratories on Earth are recreating the conditions of Big Bang nucleosynthesis with particle accelerators, testing whether slight tweaks to reaction rates could explain the missing lithium. Meanwhile, astronomers are scouring the atmospheres of the universe's oldest stars for anomalies, searching for any stellar process we might have overlooked. What makes this puzzle so gripping is what it represents: a tiny crack in the otherwise flawless edifice of Big Bang theory. If the solution requires new physics, it could open doors to realms of particle behavior we've never imagined. And if it's something more mundane, it'll force us to rethink how stars evolve over cosmic time. Either way, the lithium discrepancy isn't just about missing atoms. It's a whisper from the universe's first moments, challenging us to listen more carefully. Cosmic inflation sounds like the ultimate magic trick, the universe expanding faster than light itself in less than a trillionth of a second, smoothing out wrinkles in space-time and planting the seeds for galaxies. It's the cornerstone of modern cosmology, explaining everything from the universe's large-scale structure to the eerie uniformity of the cosmic microwave background. Yet for all its explanatory power, inflation has a dirty little secret. We've never directly observed it happening. The evidence remains tantalizingly indirect, like reconstructing a storm from the scattered debris it left behind. The hunt for smoking gun proof centers on primordial gravitational waves, ripples in space-time that inflation should have generated as space stretched violently. These waves would leave a distinctive curl pattern in the polarization of the cosmic microwave background, a faint fingerprint known as B modes. When researchers at the BICEP 2 telescope announced they'd spotted this signal in 2014, it made global headlines. Then came the crushing realization: interstellar dust in our own galaxy could mimic the same pattern. The detection was a false alarm, and the waves remain elusive. But the frustration runs deeper. Inflation isn't a single theory, it's a family of models, each proposing different expansion speeds, durations, and energy scales. Some versions predict gravitational waves strong enough to detect with current technology, while others make waves so feeble they'll forever evade observation. Without knowing which model is correct, we're left playing cosmic roulette, building ever more sensitive detectors without guarantees. Worse still, inflation's very flexibility starts to feel like a flaw. The theory can explain almost any observed feature of the universe by tweaking parameters, so much so that critics argue it's become unfalsifiable. Want a universe with more galaxies? Adjust the inflation energy higher, fewer, dial it down. This anything-goes quality leaves some wondering if inflation is profound physics or just a clever narrative we've grafted onto the unknown. Yet the case isn't closed. Next-generation experiments like the Simons Observatory and CMB-S4 are hunting for B modes with 10 times the precision, while space-based detectors like LISA might catch gravitational waves from later cosmic epochs that indirectly test inflation's predictions. Some theorists are even exploring radical alternatives like bouncing universes or emergent spacetime, though none yet match inflation's explanatory breadth. The irony is thick. The process that allegedly shaped everything we see remains just out of view. Solving this mystery won't just validate or overturn a theory, it'll force us to confront whether the universe's origin story is knowable at all, or if some chapters are written in ink we'll never learn to read. There's a crack in the universe's facade, an unsettling pattern etched into the oldest light we can see. Scientists call it the axis of evil, a name that sounds ripped from a cosmic thriller, but the reality is even stranger. When we map the cosmic microwave background, the faint afterglow of the Big Bang, we expect randomness, a speckled tapestry of hot and cold spots with no particular order. Instead, the data reveals something that defies explanation. Certain fluctuations align along an invisible line stretching across the sky, as if the universe itself picked a favorite direction. This isn't just a statistical quirk. The alignment challenges one of cosmology's sacred principles, the Copernican idea that no place or direction in space is special. If the axis is real, it implies a cosmic anisotropy, a preferred orientation woven into the fabric of reality. Some regions of the early universe might have expanded faster than others, or perhaps an unseen force tugged at spacetime before inflation could smooth everything out. The implications are staggering. Our universe could have a tilt, a hidden asymmetry that rewrites the rules we thought were universal. Skeptics argue it's an illusion, a fluke of measurement or incomplete data. After all, the cosmic microwave background is incredibly faint, and filtering out interference from our own galaxy's dust and radiation is like trying to hear a whisper in a hurricane. But the axis persists across multiple missions, from WMAP to Planck, with odds of it being random as low as 1 in 10,000. That's not quite proof, but it's enough to keep physicists awake at night. The wildest theories emerge from the shadows. Could the axis be a fossil imprint of a universe before ours, a scar left by some cataclysmic collision in a multiverse? Or is it evidence of dark energy's grip tightening unevenly, stretching space-time like taffy in one direction? Some even toy with the idea that we're seeing the wake of a colossal structure beyond our observable horizon, something so vast its gravity warps the primordial glow. What makes the axis of evil so provocative isn't just the anomaly itself, it's the reminder that the cosmos might still be hiding its deepest rules. Every time we think we've cracked the universe's code, it throws a curveball, whispering that there's more to the story. Until we solve this riddle, the axis stands as a silent challenge. The universe isn't just stranger than we imagine, it might be stranger than we can imagine. The universe began with a whisper, not the thunder of galaxies colliding or stars igniting, but the faintest tremors in the quantum foam, fluctuations so tiny they'd vanish in a heartbeat. Yet these microscopic ripples, born in the first sliver of a second after the Big Bang, became the blueprint for everything we see today, the cosmic web with its glittering galaxies and yawning voids. That's just quantum physics writ large, stretched across space and time by inflation's relentless pull. Here's the staggering part: those initial fluctuations were ridiculously small. Picture a subatomic roller coaster where particles pop in and out of existence, creating density variations smaller than a proton. Inflation magnified those differences exponentially, turning quantum fuzz into cosmic mountains and valleys. Gravity did the rest, pulling matter into the denser regions over billions of years until they became galaxy clusters, while the emptier zones stretched into vast cosmic deserts. But the plot thickens when we compare predictions to reality. The math says these quantum seeds should follow a predictable pattern called a Gaussian distribution, essentially randomness with rules. Yet when astronomers map the universe's large-scale structure, they find subtle deviations. Some galaxy clusters are clumpier than expected, while voids appear eerily smooth. It's as if an unseen hand tweaked the dice rolls of the early universe, favoring certain outcomes. One leading suspect: primordial magnetic fields generated during inflation that could have nudged particles into unexpected configurations. Others point to exotic dark matter interactions or even remnants of higher dimensional physics leaking into our 3D world. The most tantalizing clue comes from the cosmic microwave background, where certain temperature fluctuations seem slightly too pronounced, hinting that quantum fluctuations might not have been entirely random, but influenced by forces we haven't yet imagined. The irony is delicious. The largest structures in existence owe their shape to the tiniest, most fleeting events, and that's where the mystery deepens. If quantum fluctuations truly built the cosmos, why don't our simulations match what we observe? Could there have been multiple waves of fluctuations, some erased by cosmic inflation while others survived? Or does dark energy's repulsive force now stretching the universe apart somehow trace back to those first quantum shivers? Every new galaxy survey adds pieces to the puzzle. Projects like DAISY and Euclid are mapping millions of galaxies with unprecedented precision, tracing the invisible threads of dark matter that grew from those quantum seeds. Meanwhile, physicists are recreating conditions of the early universe in supercolliders, hunting for particles or fields that might have tilted the playing field. What's at stake isn't just a technical detail, it's the origin of structure itself. If we crack this code, we'll know whether the universe's architecture was inevitable or a fluke, whether other cosmic webs would look eerily similar or wildly different. And that answer hides in the ghostly imprint of quantum uncertainty, written across the night sky in stars and galaxies. The early universe had no business being this tidy. When we look at the cosmic microwave background, the oldest light in existence, we're greeted by a scene of eerie calm. Temperatures vary by less than 1 part in 10,000 across the entire sky, as if someone took a cosmic iron to space-time before the first stars even flickered on. This extreme smoothness defies intuition. After all, the newborn universe was a seething, chaotic place where quantum fluctuations and violent energy shifts should have left it dramatically lumpy. So how did everything end up so astonishingly even? The leading explanation is cosmic inflation, that brief but mind-bending moment when the universe expanded faster than light itself, stretching quantum wrinkles into cosmic proportions. Think of blowing up a balloon with microscopic dots on its surface. As it inflates, those dots grow farther apart and their variations smooth out, leaving behind a nearly uniform canvas. Inflation did the same to space-time, turning subatomic roughness into continent-scale undulations too gentle to disrupt the overall harmony. But this elegant solution comes with wrinkles of its own. Some models of inflation predict slightly more clumpiness than we observe, while others suggest the universe should be even smoother. The Goldilocks precision of the actual measurements, neither too rough nor too flat, hints that inflation might not be the whole story. Could some unknown process have ironed out irregularities after inflation ended? Or does dark matter play an unexpected role in suppressing cosmic unevenness? The plot thickens when we zoom in. While the universe appears smooth on the largest scales, closer examination reveals a hierarchy of structure galaxies clustered into filaments and walls separated by vast voids. This cosmic web suggests that while inflation set the stage, other actors stepped in to sculpt the details. Dark matter's gravitational pull likely amplified certain density variations while leaving the broader landscape intact, like waves rippling across an otherwise still pond. Yet even this layered explanation can't account for everything. Certain regions of space, like the controversial cold spot in the cosmic microwave background, show unexpected smoothness on scales that challenge standard theories. Some researchers speculate these anomalies might be scars from collisions with other universes in the multiverse, while others propose exotic physics like decaying dark energy particles that briefly froze space-time's evolution. The universe's smoothness isn't just a curiosity, it's a forensic clue. If the early cosmos had been even slightly more uneven, matter would have clumped too quickly, forming monstrous black holes instead of galaxies. A tad smoother, and gravity might never have gathered enough material to light the first stars. This delicate balance suggests that inflation, if it happened, was fine-tuned in ways we don't yet understand. Or perhaps, as radical alternatives like loop quantum cosmology propose, the universe never needed inflation at all, and its smoothness comes from a deeper quantum origin. Every new sky survey adds pieces to this puzzle. Observatories measuring the polarization of the cosmic microwave background or mapping millions of galaxies in 3D are testing whether the smoothness holds at even finer scales. The answer could rewrite our origin story, revealing whether the universe's serene beginnings were inevitable or a cosmic roll of the dice that, against all odds, came up just right. Gravitational waves aren't just cosmic messengers, they could be time travelers. While we've detected ripples from black hole collisions and neutron star mergers, the ultimate prize remains hidden. Primordial gravitational waves, vibrations sent spiraling through space-time from the very instant of the Big Bang itself. These waves wouldn't just be old, they'd be relics from before time as we know it began, carrying secrets about the universe's violent birth. The challenge is finding them. Unlike the sleek, rhythmic waves produced by modern cosmic collisions, primordial waves would be a chaotic chorus, stretched and distorted by inflation into a faint, omnidirectional hum. Imagine trying to hear a single note in a symphony played at the bottom of the ocean while wearing earmuffs. That's the scale of the problem, yet the payoff would redefine physics. These waves could prove inflation happened, reveal the energy scale of the early universe, and even hint at quantum gravity's elusive nature. Current efforts focus on two fronts. First, the cosmic microwave background. Inflationary gravitational waves should have left a distinctive swirling pattern be modes in the polarization of this ancient light. Ground-based telescopes like BICEP and the Simons Array scan the skies from Antarctica's dry, stable air, while future space missions aim to eliminate interference from galactic dust. The second approach, pulsar timing arrays, networks of ultra-precise cosmic clocks, millisecond pulsars act as a galaxy-sized detector. As gravitational waves pass through, they subtly alter the timing of pulsar flashes, creating a detectable pattern over decades. But here's the twist: the longer we search without definitive detection, the more perplexing the implications. Some inflation models predicted waves strong enough to have been spotted by now. Their absence forces physicists to consider alternatives. Maybe inflation occurred at lower energies, or perhaps it didn't happen at all. Wildcard theories gain traction, like bouncing cosmologies where the Big Bang was a rebound from a prior collapse, leaving no inflationary waves to find. The stakes transcend academic curiosity. Primordial waves could answer why our universe exists at all. One theory suggests they might bear fingerprints of cosmic strings, hypothetical defects in space-time left over from the early universe's symmetry breaking. Others speculate they could reveal extra dimensions, their unique signatures warped by hidden folds in reality. Or they might expose the quantum nature of gravity itself, showing how space-time behaves when shredded to its smallest scales. Every null result tightens the constraints, pushing theorists to invent ever more clever models. Meanwhile, detectors grow more sensitive. The upcoming Cosmic Microwave Background Stage 4 experiment promises 10 times the precision of current setups, while next-gen pulsar arrays expand to include hundreds of stars. The race isn't just about technology, it's a philosophical battleground. Do we live in a universe that leaves detectable traces of its origin, or one that guards its ultimate secrets forever? The silence so far might be a cosmic lesson. Some answers aren't handed to us. They're etched into the fabric of reality, waiting for the right moment and the right minds to uncover them. Whether we find these waves or not, the search itself is reshaping our understanding of existence, one fleeting vibration at a time. Black holes weren't just cosmic vacuum cleaners in the early universe. They were information shredders, tearing apart the very rules we thought governed reality. This is the black hole information paradox, a puzzle so profound it forces us to question whether the fundamental laws of physics break down at the edge of a singularity. And when we apply it to the primordial black holes that might have existed in the universe's first moments, the paradox becomes even more bewildering. According to quantum mechanics, information, the detailed state of every particle, can never truly be destroyed. It might get scrambled beyond recognition, but in principle it should always be recoverable. Yet black holes seem to flaunt this rule. When matter falls in, it's crushed into oblivion at the singularity, leaving behind only three observable properties: mass, spin, and charge. Everything else, the composition of the star that formed it, the atoms of an unlucky astronaut, even the quantum states of particles, appears irretrievably erased. Stephen Hawking's famous discovery that black holes slowly evaporate through radiation only deepens the mystery. This Hawking radiation seems random, carrying no trace of the information swallowed by the black hole. If that's true, the universe has a serious accounting problem. Now, imagine this scenario playing out with the first black holes to exist. Unlike modern black holes, which form from collapsing stars, primordial black holes could have been born in the chaos of the early universe's density fluctuations, some as small as asteroids, others as massive as galaxies. If these ancient black holes evaporated via Hawking radiation, as the smallest ones should have by now, did they take countless secrets of the early cosmos with them? The radiation they emitted would be the only remnant of their existence, but if it's truly random, it's like burning a library and claiming the smoke carries the contents of every book. The stakes get even higher when we consider quantum gravity. Some theories suggest that information isn't lost but encoded in ways we can't yet decipher, perhaps on the event horizon itself, like a cosmic hologram. Others propose that black holes are portals to other universes, with information leaking into hidden dimensions. But primordial black holes throw a wrench into these elegant solutions. Their extreme environments and potential interactions with exotic early universe physics might have scrambled information beyond even these theoretical recovery mechanisms. Recent breakthroughs add tantalizing twists: the holographic principle, the idea that all information within a volume of space can be represented on its boundary, gains traction when we study how early black holes might have imprinted data on the fabric of space-time itself. Meanwhile, simulations of quantum entanglement suggest that Hawking radiation might not be random after all, but subtly correlated in ways that preserve information over astronomical timescales. Yet primordial black holes refuse to fit neatly into any one theory. If they formed in clusters or evaporated asymmetrically, their information echoes could be smeared across the cosmos, making them even harder to decode. Some physicists now speculate that the paradox isn't a flaw in our understanding but a clue, a sign that the early universe operated by different quantum rules, or that information is stored in forms we haven't yet imagined, like knots in space-time or vibrations of cosmic strings. The unsettling truth: we might need a black hole time machine without observing the evaporation of an actual black hole, or uncovering relics of primordial ones. The paradox remains open. Every proposed solution, from firewalls to fuzzballs, feels like a piece of a puzzle we're assembling in the dark. But this isn't just academic gymnastics. Crack the paradox and we might unlock the universe's deepest cipher: how it preserves its past and whether reality itself is as permanent as we believe. The universe has a strange habit of remembering its past but forgetting its future, a phenomenon we call the arrow of time. From the way coffee cools to the way stars burn out, everything seems to obey this rule: entropy or disorder always increases. But here's the cosmic head-scratcher. If entropy only grows over time, why was the early universe in a state of bizarrely low entropy to begin with? It's like finding a perfectly stacked house of cards in the middle of a hurricane and realizing the storm must have built it. Picture the Big Bang's aftermath: a searing, dense soup of particles so uniform that physicists describe it as having nearly zero entropy. This shouldn't make sense. High entropy means chaos, like a shattered glass, while low entropy implies meticulous order, like a pristine ice crystal. So why did the universe start in such an improbably tidy state, only to spend the next 13 billion years unraveling? The answer might lie in gravity's hidden role. While we typically associate entropy with disorder, spilled milk, scattered papers, gravity flips the script. Under its pull, a cloud of gas isn't at maximum entropy when it's evenly spread out, but when it's collapsed into black holes, the ultimate cosmic trash compactors. The early universe's smoothness wasn't order at all, but a state of unrealized potential, like a coiled spring waiting to unleash chaos in the form of galaxies and stars. But gravity alone doesn't solve the puzzle. Some theorists suggest the real answer lies beyond our universe, in the multiverse. If our cosmos is one of countless bubbles in an eternally inflating sea, it might have simply inherited its low entropy as a statistical fluke, a rare pocket where conditions were just right for time's arrow to emerge. Others propose darker ideas, like quantum entanglement between our universe and a hypothetical mirror universe moving backward in time, creating a delicate balance that set entropy on its one-way march. The implications aren't just philosophical. If we've misunderstood time's origins, it could rewrite the fate of everything. Black holes, dark energy, even the universe's eventual heat, death, all hinge on entropy's unshakable rule. And if that rule has an exception lurking in the cosmic dawn, the arrow of time might not be an absolute after all. It could be a fleeting signature of how our universe was born, destined to fade when the last stars blink out and space becomes too vast for even memories to survive. Look at any corner of the night sky, and you'll find the same cosmic recipe, the same ratio of hydrogen to helium, the same temperature fluctuations, the same fundamental forces at work. But here's what doesn't add up. Regions of the universe so far apart that light hasn't had time to travel between them since the Big Bang somehow share these exact same properties. It's like walking into two separate bakeries on opposite sides of the planet and finding identical loaves of bread, down to the number of sesame seeds on the crust, despite the bakers never having met or shared a recipe. This is the horizon problem, one of cosmology's most baffling puzzles. To grasp why this is so strange, imagine the universe as a growing balloon. Two dots painted near each other can exchange information easily, but dots on opposite sides are forever out of touch because the space between them expands faster than light can cross it. In the early universe, this separation happened on enormous scales. Regions now billions of light years apart were once close enough to interact, but only for a sliver of time after the Big Bang, far too brief for any physical process to synchronize their properties. Yet when we examine these regions today, they're statistically identical, as if orchestrated by some unseen hand. Enter cosmic inflation, the leading solution to this riddle. This theory proposes that the universe underwent a period of exponential expansion in its first fraction of a second, stretching a tiny, homogeneous patch of space larger than we can observe today. Before inflation, all parts of this patch were close enough to exchange heat and information, reaching equilibrium like a cup of coffee cooling to room temperature. Then inflation kicked in, locking that uniformity in place as space itself ballooned faster than light could traverse it. The result, a universe that looks coordinated across vast distances without any direct communication. But inflation isn't the only game in town. Some physicists explore alternatives like variable speed of light theories, where light traveled much faster in the early universe, allowing distant regions to sync up before settling into today's constant. Others propose a bouncing cosmology, where the Big Bang was preceded by a collapse that naturally ironed out irregularities. Then there's the truly mind-bending idea of entanglement across space-time, where quantum connections forged at the birth of the universe maintained correlations even as space expanded. The horizon problem isn't just academic, it's a litmus test for our understanding of cosmic origins. If inflation is correct, its imprint should be hiding in the faint polarization patterns of the cosmic microwave background or the distribution of galaxies. But if another mechanism is at work, we might need to rethink the universe's very first moments, and with them, the rules we thought governed reality. Every observation tightens the noose around these theories, forcing us to confront whether the universe's uniformity is a clue or the ultimate cosmic sleight of hand. Magnetic monopoles should be everywhere, hiding in plain sight, tucked into the fabric of reality like cosmic needles in a haystack. According to grand unified theories, which aim to merge the fundamental forces of nature, these elusive particles, magnets with just a north or south pole, never both should have been produced in staggering numbers during the universe's first moments. The math is clear. As the fiery chaos of the early cosmos cooled, phase transitions in the underlying field should have left behind defects, knots in space-time where monopoles formed like cracks in freezing ice. Billions upon billions of them, so many that their collective mass would outweigh all the stars and galaxies we see today. Yet here's the cosmic sleight of hand: we've never found a single one. Not in particle colliders, not in ancient meteorites, not even in the moon's dusty soil where they might have lingered undisturbed for eons. It's as if the universe played a trick on us, dangling a prediction so compelling that its absence forces us to question everything we think we know about physics' most elegant theories. The most popular escape hatch: cosmic inflation. If the universe expanded exponentially fast in its first sliver of a second, as inflation suggests, it could have stretched space-time so thin that monopoles were diluted to near nothingness, scattered so far apart that spotting one becomes a statistical miracle. Imagine blowing up a balloon covered in confetti until the dots are light years apart. That's inflation's proposed cleanup job, but this solution comes with its own baggage. If inflation erased monopoles, why didn't it smooth out everything else, like the quantum fluctuations that seeded galaxies? And why do some refined versions of grand unified theories still predict monopole densities just below our detection threshold, teasing us with the possibility they're out there, waiting to be discovered? Then there's the wild card. Maybe monopoles aren't elementary particles at all, but composite objects, bound states of other particles that only reveal their true nature under conditions we haven't yet recreated. Some theories suggest they're so massive, perhaps a quadrillion times heavier than a proton, that they'd require energies far beyond any human-made collider to produce. Others propose they decayed into other particles long ago, leaving behind only faint traces in the cosmic microwave background or neutrinos with unusual energies. The hunt isn't over. Hidden in the data of underground detectors like Mo-Edel or etched into the paths of cosmic rays, there might be clues we've overlooked. Every null result tightens the noose, forcing theorists to invent ever more clever models where monopoles exist just beyond our grasp, trapped in higher dimensions, shielded by exotic forces, or lurking in the hearts of neutron stars where their magnetic fields could twist spacetime itself. What makes this mystery so thrilling isn't just the missing particles, it's what their absence reveals about the universe's ability to defy our grandest theories. Solve it and we might unlock the next chapter of physics. Fail and we'll have to rewrite the book altogether. What if the laws of physics weren't always set in stone? For decades, scientists have operated under the assumption that the fundamental constants of nature, those unchanging numbers that dictate how particles interact, have remained rigid since the dawn of time. But a series of controversial observations has thrown this certainty into doubt, particularly when it comes to one of the most delicate balances in the cosmos, the fine structure constant. This seemingly innocuous number, roughly equal to 1/137th, governs the strength of electromagnetic interactions between charged particles. It's the reason atoms hold together, light exists, and chemistry works at all. Yet multiple studies of light from distant quasars, absorbed by ancient gas clouds billions of years ago, suggest this constant might have been ever so slightly different when the universe was young. The evidence comes from spectral lines, those dark fingerprints in starlight where specific wavelengths are absorbed by elements like iron or magnesium. When researchers analyze light that's traveled for over 12 billion years, they find these lines don't align perfectly with the patterns we see in labs on Earth. The shifts are minuscule, just a few parts in a million, but if real, they'd imply the fine structure constant was weaker or stronger in the past. Imagine tuning a piano only to discover its notes subtly drifting over time, revealing that the very essence of sound isn't as fixed as you believe. That's the scale of what's being proposed here, a crack in the foundation of physics itself. Skeptics argue these results could be artifacts of measurement errors or unknown astrophysical processes. After all, interpreting quasar light is like reconstructing a symphony from echoes bouncing through a maze. Dust, magnetic fields, or even the motion of gas clouds could mimic the signal of a changing constant. But the data persists across multiple independent studies, using different telescopes and methods, with some regions of the sky showing stronger variations than others. This patchiness fuels even wilder speculation. Could the constant vary not just over time, but across space? The implications are staggering. If constants evolve, the universe's rulebook isn't written in permanent ink. It might be more like a draft with revisions scribbled in the margins. Some theories, like string theory, actually predict extra dimensions that could cause constants to fluctuate as the universe expands. Others suggest dark energy's influence might alter fundamental physics over cosmic timescales. But here's the unsettling twist. even a tiny change in the fine structure constant would have made stars burn differently, chemistry behave unpredictably, and life as we know it potentially impossible. The fact that we exist to measure it might mean we're living in a privileged era, or worse, that we're fundamentally limited in our ability to perceive a cosmos where the rules aren't what they seem. The debate is far from settled. Next-generation telescopes like the Extremely Large Telescope aim to measure these spectral shifts with unprecedented precision, while lab experiments with atomic clocks search for flickers of change over mere decades. Whether the constants are truly varying or not, the mere possibility forces us to confront a humbling truth. The universe's deepest laws might still have secrets we've barely begun to uncover. What makes this mystery so profound isn't just the potential discovery, it's the door it opens. If one constant can vary, others might too, rewriting our understanding of everything from black holes to the Big Bang. The cosmos has never been shy about defying our expectations, and this could be its quietest, most radical rebellion yet. Quantum gravity should have left its fingerprints all over the early universe, bold, unmistakable smudges in the fabric of reality. At the densities and temperatures of the cosmos's first moments, gravity wasn't just another force. It was a quantum beast flickering in and out of existence, warping space-time on scales so tiny they defy imagination. Yet when we scour the cosmos for traces of this primordial quantum gravity, effects that should have imprinted on the cosmic microwave background, the distribution of galaxies, or even the very laws of physics, we find nothing. It's as if the universe played the ultimate magic trick, erasing all evidence of its own deepest workings. The problem starts with scale. In the early universe, where matter was packed into a space smaller than an atom, quantum fluctuations in gravity itself should have been as common as ripples on a pond. These fluctuations would have tangled with other quantum fields, potentially leaving behind relics like primordial gravitational waves with unique signatures or subtle twists in how matter clumped together. Some theories even predict that space-time itself might have been foamy at these scales, bubbling with virtual black holes and wormholes that flickered in and out of existence. But when we look for these hallmarks in the cosmic microwave background's temperature variations or the large-scale structure of galaxies, the data remains stubbornly smooth. It's like searching for footprints in wet cement only to find the surface perfectly untouched. One leading explanation is that cosmic inflation. The universe's exponential expansion in its first fraction of a second stretched these quantum gravitational effects so thin they became undetectable. Imagine scribbling a message on a balloon, then inflating it to the size of a planet. The words would vanish into invisibility. But this raises its own paradox. If inflation was powerful enough to erase quantum gravity's fingerprints, why did it leave behind the quantum fluctuations that seeded galaxies? The selectivity feels suspicious, as if the universe curated which quantum effects we're allowed to see. Another possibility cuts deeper. What if we're looking for the wrong thing? Most searchers assume quantum gravity would manifest as tiny corrections to Einstein's relativity, like faint static over a radio signal. But if gravity behaves completely differently at quantum scales, say, through loops, strings, or emergent spacetime, its early universe signature might not match any template we've devised. It's like trying to reconstruct a symphony by listening only for violins, missing the cellos, horns, and drums entirely. Some models suggest quantum gravity could have imprinted not on space-time's geometry, but on the very nature of dark matter or dark energy, hiding in plain sight within mysteries we've already catalogued but don't yet understand. The silence isn't just a scientific challenge, it's a philosophical provocation. If quantum gravity shaped the universe's birth but left no trace, does that mean its effects are inherently unobservable? Or are we, like fish trying to describe water, simply too embedded in the system to perceive its foundational quirks? The answer might lie in the next generation of experiments, atom interferometers hunting for fuzzy space-time, pulsar timing arrays sensitive to ancient gravitational waves, or even tabletop experiments probing gravity's quantum nature directly. Until then, the absence of quantum gravity's signature isn't just a missing piece, it's a mirror held up to our assumptions, revealing how much we still don't know about the universe's first whispers. The Big Bang should have been the ultimate equalizer, a perfect cosmic balance where matter and antimatter were created in equal amounts, destined to annihilate each other in bursts of pure energy, leaving behind an empty, lifeless void. Yet here we are, in a universe filled with galaxies, stars, and planets made of matter, with hardly any antimatter in sight. This isn't just a slight imbalance, it's one of the most glaring contradictions in modern physics. If the laws of nature treat matter and antimatter as near-perfect mirror images, why did matter win the cosmic lottery? To understand the scale of the problem, consider what should have happened in those first moments. Every particle of matter, every proton, every electron should have been paired with its antimatter counterpart. When they meet, they annihilate in a flash of gamma rays, leaving nothing behind. If the universe had truly been symmetric, all matter and antimatter would have cancelled each other out, leaving a sea of radiation with no structure, no chemistry, no us. The fact that we exist means something tipped the scales. The search for this cosmic cheat code leads us to a concept called charge parity violation, or CP violation for short. In simple terms, it means the universe might have a subtle preference for matter over antimatter in certain rare interactions. Physicists first glimpsed this asymmetry in the 1960s, studying particles called kaons, which decayed slightly differently than their antimatter versions. The effect was tiny, a fraction of a percent, but it proved the universe wasn't perfectly symmetrical. Later experiments with other particles, like B mesons, found similar imbalances, but none of them were nearly large enough to explain the overwhelming dominance of matter we see today. This leaves us with two unsettling possibilities. Either there's a much stronger source of CP violation we haven't discovered yet, something that acted in the extreme conditions of the early universe and then faded, or our understanding of antimatter's behavior is fundamentally incomplete. Some theories propose that super-heavy particles, existing only in the first moments after the Big Bang, decayed unevenly, dumping extra matter into the cosmic mix before vanishing. Others suggest that antimatter might have segregated into hidden regions of space, forming vast, invisible anti-galaxies we've yet to detect, the most radical idea. Antimatter might not be as perfectly mirrored as we think. If gravity affects it differently, if antimatter falls upward instead of down, for instance, that could have led to an early separation, allowing matter to dominate by default. Experiments like those at CERN Alpha facility are now testing this by precisely measuring how antimatter behaves in gravitational fields. The stakes couldn't be higher. Solve this puzzle, and we might finally understand why the universe didn't vanish into pure energy before it even began. Fail, and we're left with a gaping hole in our origin story, a silent reminder that the cosmos still holds secrets too profound for our equations to capture. One thing's certain, the answer, when we find it, won't just explain the past, it'll redefine the future of physics itself. Hidden in the static of the cosmic microwave background, the faint echo of the Big Bang, lies an anomaly so strange it defies easy explanation. Stretching across a vast swath of sky, the so-called cold spot appears as a region slightly cooler than its surroundings, a cosmic bruise that shouldn't exist according to standard cosmology. At first glance, temperature variations in the ancient light aren't unusual. The early universe was a turbulent place, filled with ripples that eventually grew into galaxies. But this spot is different, larger and colder than statistical models predict. Its presence is like finding a frozen lake in the middle of a desert, the odds of such a feature arising naturally. Less than 1 in 50. So what carved this icy fingerprint onto the fabric of the cosmos? One provocative theory suggests the cold spot might be a collision scar, a bruise left by our universe bumping into another bubble of reality in the multiverse. Picture two soap bubbles grazing each other in a sink, their surfaces briefly warping at the point of contact. If another universe existed alongside ours during inflation, the energy of that encounter could have drained heat from that patch of space, leaving behind a chill we now detect billions of years later. It's a radical idea, but not without precedent. The math of inflation naturally predicts the existence of other universes, each with their own physics, forever out of reach except perhaps through ghostly imprints like this one. Yet not everyone buys the multiverse explanation. Skeptics argue the cold spot could be a rare but natural fluctuation, a cosmic roll of the dice that just happened to land on an improbable outcome. Others propose more grounded, though no less bizarre alternatives. Could a supervoid, an enormous region of space nearly empty of galaxies and dark matter, be pulling light passing through it like a gravitational magnifying glass in reverse? This integrated Sachs-Wolf effect would subtly redshift the cosmic microwave background, making the region appear colder. The problem: surveys haven't found a void large enough to explain the anomaly, leaving the theory dangling. Then there's the wild card: topological defects. In the early universe, as fundamental forces separated from their primordial unity, cracks might have formed in space-time itself, cosmic strings or textures that warped the surrounding energy. If one of these defects lingered near the spot where the cold spot now sits, it could have distorted the microwave background in ways we're only beginning to model. The challenge: no one has ever detected such a defect directly, making this explanation as speculative as the multiverse hypothesis. What makes the cold spot so compelling isn't just its strangeness, it's the way it forces us to confront the limits of our cosmic maps. If it's a statistical fluke, it's a reminder that even the most precise theories can't account for every quirk of reality. If it's evidence of a multiverse or exotic physics, it's a glimpse beyond the curtain of our observable universe, hinting at realms we've barely imagined. Either way, this icy enigma refuses to be ignored, challenging us to ask: are we reading the universe's history correctly, or is there a whole chapter we've missed? Future telescopes like the Simons Observatory aim to study the cold spot with unprecedented resolution, hunting for subtle polarization patterns or secondary anomalies that could break the stalemate between theories. Until then, it remains one of cosmology's most tantalizing Rorschach tests, a blot on the sky that reveals as much about our scientific ambitions as it does about the universe's hidden architecture. Every second, trillions of ghostly particles pass straight through your body, silent, unseen, leaving no trace. These are primordial neutrinos, relics from the universe's first second, when temperatures were so extreme that these lightweight particles flooded space in numbers dwarfing even the stars. Today, they should form an invisible sea, saturating every cubic centimeter of the cosmos, with roughly 300 neutrinos left over from the Big Bang. Yet despite their staggering abundance, we've never detected a single one directly. It's as if the universe left us a voicemail from its birth, but we're stuck with a broken phone. The problem isn't that neutrinos are rare, it's that they're shy. Born in the furnace of the early universe, these particles interact so weakly with matter that a neutrino could slice through a light year of lead without slowing down. Modern detectors like supercamioc and catch neutrinos from the sun or supernova by sheer luck, relying on vast tanks of ultra-pure water where, once in a blue moon, a neutrino might bump into an atomic nucleus and produce a faint flash of light. But primordial neutrinos are a different beast. While their modern cousins carry enough energy to trigger these rare interactions, the ancient ones have been stretched and cooled by the expanding universe, their energies now so low that they slip through every net we've devised. This creates a paradox. The very thing that makes neutrinos fascinating, their ability to ignore almost everything, also makes them nearly impossible to study. Imagine trying to catch fog with a fishing net. The holes are simply too big. Even if we built a detector the size of a planet, the odds of capturing one of these cosmic ghosts would be vanishingly small. Yet the stakes couldn't be higher. These neutrinos aren't just passive relics, they're time capsules holding secrets about the universe's earliest moments. Their exact energies and numbers could reveal whether the Big Bang unfolded as smoothly as we think, or if violent phase transitions, like bubbles popping in spacetime, altered their paths. Some theories even suggest that primordial neutrinos might have subtly influenced how matter clumped together, leaving faint fingerprints in the cosmic web of galaxies we see today. The hunt isn't hopeless. Scientists are devising clever workarounds, like searching for minuscule distortions in the cosmic microwave background caused by neutrino pressure in the early universe. Others propose tabletop experiments using ultra-cold materials where the collective jostling of atoms might betray a neutrino's whisper-thin touch. And then there's the wild card. If these neutrinos have even a tiny mass, something modern physics allows, they might have slowed just enough over billions of years to become detectable by next-generation sensors. Until then, this invisible ocean remains one of cosmology's great unsolved riddles. Its existence is etched into our theories, its influence woven into the fabric of reality, yet it taunts us, a shadow from the dawn of time that refuses to step into the light. The day we finally capture one won't just solve a mystery, it'll open a window to a world we've only ever dreamed of seeing. What if our universe is just one frothy bubble in an endless cosmic sea? The bubble universe hypothesis paints a startling picture, an infinite multiverse where each reality exists as its own expanding pocket, floating in a vast, energetic ocean. These bubbles don't pop like soap suds. They're self-contained universes with their own unique physics, born from the same primordial quantum foam that birthed our own. And the wildest part, the echoes of that violent birth might still linger in the faintest signals from the early cosmos. Take cosmic inflation, the theory that our universe underwent a rapid expansion in its first moments. If inflation can happen once, why couldn't it happen endlessly, spawning countless other universes in the process? Picture a boiling pot of water, with steam bubbles constantly forming and rising to the surface. In this analogy, each bubble is a universe pinched off from the greater quantum field as it cools, its physical laws frozen into place by chance. Some bubbles might have stronger gravity, others no electrons, or even extra dimensions coiled too tightly for us to perceive. The real kicker, we might already have evidence. The cosmic microwave background, that ancient light from the universe's infancy, holds subtle anomalies like the infamous cold spot, that some theorists argue could be bruises from collisions with other bubble universes. Imagine two soap bubbles gently touching. The point of contact would leave a faint circular distortion. If another universe grazed ours during inflation, the energy of that collision could have left a detectable imprint, a too-cold patch, an unnatural void, or even strange polarization patterns in the microwave background. But proving this isn't simple. Alternative explanations exist for every anomaly, from statistical flukes to overlooked astrophysical processes. Even if we found a smoking gun, like a bizarre ring of temperature variations in the cosmic microwave background, skeptics would demand more. After all, extraordinary claims require extraordinary evidence, and the multiverse is about as extraordinary as it gets. Yet the bubble universe hypothesis isn't just wild speculation. It emerges naturally from string theory and quantum field equations, offering solutions to nagging problems like the fine-tuning of our universe's constants. Why is gravity so perfectly calibrated for galaxies to form, or the cosmological constant so eerily balanced? In a multiverse, we're just the lucky winners of a cosmic lottery, living in a bubble where the numbers lined up for life. Other universes might have collapsed instantly or torn themselves apart, never getting the chance to ask questions. The search for proof is pushing telescopes and supercomputers to their limits. Next-generation observatories will map the microwave background with pixel-perfect precision, hunting for telltale signatures like concentric rings of temperature shifts that could betray a long-ago collision. Others are simulating bubble universe formation, tracing how different inflation energies would ripple through space-time. And then there's the philosophical twist. If bubbles are infinite, does that mean every possible reality exists somewhere? Copies of you reading this script in a universe where gravity pushes instead of pulls, or where time runs backward. For now, the multiverse remains a dazzling possibility, not a fact, but that's what makes it thrilling. Whether it's confirmed or debunked, the quest forces us to rethink what universe even means, and whether our cosmic home is a lone island or just one glittering droplet in an ocean of realities beyond comprehension. One thing's certain: if other bubbles are out there, they're not just alternate versions of our story. They're entirely different books written in physics we've yet to imagine. And that might be the most humbling thought of all. Gravity might not be the universal constant we've always assumed. What if it's simply the emergent byproduct of a deeper, hidden layer of reality? That's the radical premise of emergent gravity theories, which propose that gravity isn't a fundamental force at all, but an illusion that arises from the complex interactions of unseen structures woven into spacetime itself. At the heart of this idea is a bold claim: dark matter, that elusive cosmic glue, might not exist as invisible particles but as a side effect of how gravity truly operates on the grandest scales. Take Eric Verland's controversial hypothesis of entropic gravity. Imagine spacetime as a sort of hologram, where the information encoding its structure lives not in the fabric of space, but on its boundaries, like a 3D movie projected from a 2D screen. In this view, gravity emerges from the way this information becomes entangled and redistributed, much like heat spreading through a metal rod. When galaxies rotate faster than Newton's laws predict, it's not because of hidden dark matter halos, but because the universe's quantum memory subtly alters the rules of attraction in regions of low entropy. It's as if gravity itself has a learning curve, adapting its strength based on the cosmic environment. But entropic gravity isn't the only challenger. Modified Newtonian dynamics, or MUND, suggests that Newton's famous inverse square law breaks down at extremely weak accelerations like those found at the fringes of galaxies. Instead of invoking dark matter, MUND tweaks the equations so that gravity weakens less abruptly over vast distances, neatly explaining why stars in galactic outskirts orbit faster than expected. For decades, MUND was dismissed as a fringe idea until observations of certain dwarf galaxies showed rotation curves that align eerily well with its predictions, while posing headaches for traditional dark matter models. Yet the plot thickens when we zoom out further. Galaxy clusters, massive congregations of hundreds of galaxies, seem to demand some form of invisible mass to explain their gravitational lensing effects, and here, emergent gravity theories strain to keep up. Some researchers propose hybrid solutions where emergent effects dominate within galaxies, but particle-based dark matter still operates in the emptier voids between clusters. Others speculate that we're missing a cosmic feedback mechanism where gravity's emergent behavior interacts with dark energy in ways we haven't yet modeled. The stakes are higher than just rewriting textbooks. If emergent gravity is real, it would upend our understanding of everything from black holes to the Big Bang, revealing a universe where spacetime is more like a living network than a static stage. But if it fails, its very shortcomings could pinpoint exactly where and how dark matter hides, refining the hunt for this cosmic phantom. For now, the debate rages on, with each new galaxy mapped and each telescope upgrade offering fresh clues. One thing's certain: whether gravity is fundamental or emergent, the universe still has surprises tucked deep into its gravitational folds. Magnetic fields shouldn't have stood a chance in the chaos of the early universe, yet somehow they're everywhere. From the delicate spirals of galaxies to the vast voids between them, magnetism threads through the cosmos like invisible ink, shaping how stars ignite, how cosmic rays race through space, and even how planets like Earth shield themselves from deadly radiation. But here's the cosmic conundrum. According to our best models, these magnetic fields shouldn't exist at all. The universe began as a searing, electrically neutral soup of particles, a place where magnetic fields couldn't form naturally. No batteries, no currents, no obvious way to generate the first flickers of magnetism. So how did space go from magnetically barren to saturated with these unseen forces? The problem starts with scale. To create a magnetic field, you need moving electric charges, a current. In today's universe, that's easy: swirling plasma in stars, ionized gas in galaxies, even the molten iron in Earth's core. But rewind to the cosmic dawn, and the ingredients vanish. The earliest universe was too hot and dense for atoms to form, let alone sustain the orderly flows needed to spin up magnetic fields. Even after atoms coalesced, the gas was mostly neutral, with electrons tightly bound to nuclei, leaving no free charges to create currents. It's like trying to power a city with a single A battery. The raw materials just weren't there. Yet by the time we glimpse the first galaxies, magnetism is already in full swing. Their faint radio emissions betray the presence of magnetic fields 1,000,000 times stronger than anything our theories can easily explain. One leading idea involves cosmic turbulence, the violent stirring of plasma during the universe's toddler years. As the first stars and galaxies ignited, their explosive deaths might have churned the intergalactic medium, twisting weak seed fields into organized patterns through dynamo effects. But this just kicks the can down the road. Where did those seed fields come from? Some theorists point to the quirks of quantum physics. In the frenetic moments after the Big Bang, particle-antiparticle pairs constantly popped in and out of existence, and their fleeting lives could have created tiny magnetic dipoles. If inflation stretched these quantum flickers across cosmic distances, they might have seeded the universe with faint primordial fields. Others propose more exotic origins, phase transitions in the early universe where fundamental forces split apart, could have left behind defects in space-time cosmic strings or domain walls that generated magnetism as byproducts. Even black holes might have played a role, their intense gravity warping space-time in ways that spun off magnetic energy like sparks from a grindstone. The most tantalizing clues come from the cosmic microwave background. If primordial magnetic fields existed, they should have left subtle imprints on this ancient light, polarizing it in telltale swirls. So far, the signals are too faint to confirm, but next-generation telescopes like the Simons Observatory are hunting for them with unprecedented precision. Meanwhile, simulations of the early universe reveal a surprising twist. Even absurdly weak seed fields, far too feeble to detect directly, could have been amplified by the turbulent birth of galaxies, like a whisper turning into a shout after echoing through a canyon. The implications are staggering. If magnetism arose spontaneously from the void, it challenges our understanding of how order emerges from chaos. It also raises a haunting question. Are magnetic fields an accidental byproduct of cosmic evolution, or something more fundamental, a hidden dimension of physics we've yet to uncover? Every magnetized galaxy we observe is a silent witness to this mystery, a reminder that the universe's blank pages might be written in forces we're only beginning to trace. One thing's certain, solving this riddle won't just explain magnetism. It'll reveal how the cosmos weaves complexity from simplicity, turning the faintest quantum whispers into the invisible architecture of everything. Black holes weren't just lurking in the early universe, they were feasting. Within the first billion years after the Big Bang, supermassive black holes weighing billions of suns had already taken shape, their gravitational jaws gaping wide at the centers of young galaxies. This presents a cosmic timing problem so baffling it threatens to rewrite our understanding of how these monsters form. Consider the math. Under normal circumstances, a black hole grows by slowly swallowing gas and stars, a process limited by physics itself. There's only so much material that can spiral inward at any given time, a restriction called the Eddington limit, meaning even the greediest black hole should take billions of years to reach supermassive proportions. Yet JWST and other telescopes keep spotting quasars' ultra-bright black hole beacons shining brilliantly when the universe was less than 700 million years old. That's like finding a fully grown blue whale in a kiddie pool, defying every rule of biological growth. So how did they get so big so fast? One radical theory suggests these black holes didn't grow gradually, they were born big. In the ultra-dense environment of the early cosmos, massive gas clouds might have collapsed directly into black holes weighing tens or hundreds of thousands of suns, skipping the star stage entirely. Imagine a skyscraper materializing overnight without first laying a foundation. That's the scale of this cosmic shortcut. These direct collapse black holes could have served as ready-made seeds, giving subsequent growth a colossal head start. But the plot thickens when we examine the fuel supply. The early universe wasn't the orderly place we see today. It was a riot of turbulence and raw energy. Some regions might have been littered with dense clusters of massive, short-lived stars, each collapsing into smaller black holes that then merged like drops of mercury. Others could have been fed by rivers of cold gas channeled along filaments of dark matter, creating all-you-can-eat buffets for growing singularities. There's even speculation that exotic physics, like higher dimensional effects or primordial dark matter interactions, might have juiced black hole growth beyond what standard models allow. Yet the most startling clues come from the black holes themselves. Some early quasars show bizarre emission patterns suggesting they were spinning at breakneck speeds, as if revved up by mergers or freakish accretion events. Others seem embedded in galaxies with tight, dense cores, perfect environments for runaway growth. The more we study these ancient behemoths, the clearer it becomes. The early universe didn't play by the rules we've written for black hole formation. It operated on a different timescale with different physics and possibly even different pathways to creating gravity's ultimate monsters. Solving this puzzle isn't just about rewriting astrophysics textbooks, it's about understanding how the universe builds its most extreme structures under impossible deadlines. Every new observation peels back another layer, revealing a cosmic nursery where black holes didn't just grow. They erupted. Gravity, electromagnetism, the strong and weak nuclear forces. These four fundamental interactions are the pillars holding up our understanding of physics. But what if the early universe played by different rules, with a fifth force shaping reality before fading into oblivion? This isn't science fiction. Hidden in the extreme conditions of the cosmos's first moments, there might have been a temporary player on the field, a force so fleeting it left only ghostly traces in the structure of everything we see today. The idea emerges from an uncomfortable gap in our knowledge. As we peer back to the universe's infancy, a period of unimaginable density and heat, the standard model of particle physics starts to fray. Certain interactions, like how matter clumped into galaxies or why the cosmos expanded so uniformly, don't quite add up without extra ingredients. Enter quintessence, a hypothetical fifth force often invoked to explain dark energy's repulsive push in the modern universe. But in the extreme environment of the Big Bang's aftermath, this force might have been far more potent, warping spacetime in ways that left permanent scars. Some theories propose this force acted like a cosmic sculptor, selectively pulling or pushing particles in the primordial soup. Imagine a pot of boiling water where an unseen hand briefly stirs the bubbles into perfect rows. That's the kind of delicate intervention researchers are considering. One compelling candidate comes from string theory, where extra dimensions curled up as the universe cooled might have unleashed a temporary, hyperweak force, bridging the gap between gravity and quantum mechanics before vanishing as dimensions collapsed. The most tantalizing hints come from particle colliders. When physicists smash atoms at nearly light speed, they recreate conditions not seen since the universe's first trillionth of a second. Occasionally, these experiments spit out particles with unexpected energy signatures, tiny deviations from predictions that could hint at interactions beyond the standard model. If a fifth force once existed, its residual echoes might flicker to life in these extreme environments, like shadows cast by a long-extinguished flame. Yet the challenge remains: how do you look for something that's already gone? The answer might lie in the cosmic microwave background's subtle asymmetries or the way galaxies cluster on vast scales. If a fifth force tweaked gravity's grip in the early universe, those tweaks could have frozen into the distribution of matter we see today, like fossilized footprints in cosmic mud. Others suggest hunting for exotic particles that might be relics of this force, slow-moving, weakly interacting, dark photons or action-like particles that drifted through the cosmos after their parent force faded. The implications are staggering. If confirmed, a fifth force would rewrite our understanding of how the universe's fundamental laws evolved. It might explain why dark matter seems to clump differently than predicted, or why certain elements formed in unexpected abundances after the Big Bang. But until we catch its shadow in the data, this phantom force remains one of cosmology's most tantalizing what-ifs, a reminder that the universe's first moments might have been stranger than we ever imagined. Perhaps the most humbling thought: if such a force once existed, it might not be alone. The early cosmos could have hosted a zoo of temporary interactions, each flashing into existence before vanishing forever, leaving behind only whispers in the structure of reality. And those whispers might still be waiting for us to decipher them. What if the Big Bang wasn't the beginning of everything, just the latest chapter in an endless cosmic saga? The idea of a cyclic universe turns our linear timeline inside out, suggesting that space, time, and matter undergo infinite cycles of birth, death, and rebirth. In this sweeping vision, each bang is preceded by a crunch, where the universe collapses in on itself only to rebound with explosive new energy. It's a dramatic twist on the standard cosmic origin story, one that could explain some of the most puzzling features of the early universe if we know where to look. The spark for this theory comes from an unexpected place: the eerie smoothness of the cosmic microwave background. Why is the temperature of this ancient light so uniform across the sky, even in regions that could never have exchanged heat or information? Inflation offers one solution, but cyclic models propose another. If our universe inherited its structure from a previous phase of existence, a cosmos that compressed nearly to a singularity before bouncing back, the extreme conditions of that collapse might have ironed out irregularities, leaving behind the smooth slate we observe today. Think of it like kneading dough. Each cycle of compression and expansion could have homogenized the cosmic batter, erasing the lumps of the past while imprinting faint echoes of its own history. But how would such a cycle even work? One compelling framework comes from string theory, where colliding higher dimensional membranes of reality could trigger periodic cataclysms, each birthing a new universe. Another approach, loop quantum cosmology, suggests that gravity itself becomes repulsive at extreme densities, preventing total collapse and instead sparking a rebound. In both scenarios, traces of earlier cycles might linger in the arrangement of galaxies or subtle swirls in the cosmic microwave background, like fingerprints pressed into the fabric of spacetime. The hunt for evidence is already underway. Some researchers scrutinize the cosmic microwave background for anomalous circular patterns, potential bruises from collisions with other universes in a multiversal cycle. Others search for imprints of phantom fields, hypothetical energies that could drive eternal repetition. Then there's the controversial idea of conformal cyclic cosmology, championed by physicist Roger Penrose, which proposes that black holes from one era evaporate into pure radiation, seeding the next cycle's beginnings. If correct, faint concentric rings in the microwave background, dubbed Hawking points, could be the fading embers of ancient black holes from a universe long gone. Yet the cyclic model faces fierce challenges. Critics point to entropy, the relentless growth of disorder that seems to arrow irreversibly forward. If each cycle inherits the entropy of the last, the universe should grow messier with every rebirth, making the pristine conditions of our early cosmos inexplicable. Defenders counter with speculative fixes like quantum resets or entropy-shedding mechanisms, but these remain untested. What makes this idea so captivating isn't just its audacity, it's the way it reimagines time itself. In a cyclic cosmos, beginnings and endings blur into a single, eternal rhythm, where every collapse plants the seeds of a new dawn. Whether the evidence ultimately supports this vision or not, it forces us to confront a profound question. Are we living in a universe with a definitive starting gun, or just one heartbeat in an infinite cosmic pulse? The answer might be written in the faintest whispers of the sky, waiting for the right telescope or the right mind to decode it. From the cosmic shadows of dark matter to the ghostly whispers of primordial neutrinos, these 30 mysteries paint a humbling portrait of our place in the universe. For all our telescopes and supercomputers, we're still cosmic detectives piecing together a crime scene 13.8 billion years in the making. Every answer we uncover doesn't just solve a puzzle, it rips open a dozen new enigmas, like peeling an infinite onion where each layer reveals stranger patterns than the last. Take something as fundamental as the Big Bang itself. We've mapped its afterglow down to microscopic temperature fluctuations, yet we still don't know what triggered it or whether before even means anything in that searing moment of creation. Or consider dark energy. We've measured its accelerating push on the cosmos, but can't explain why its strength appears fine-tuned to impossible precision, as if the universe dialed in its own expansion rate with cosmic OCD. Even the humble neutrino, a particle so ubiquitous trillions pass through you every second, guards secrets about the universe's first second that defy our most sensitive detectors. This isn't failure, it's the thrilling frontier of discovery. Each anomaly, each stubborn mismatch between theory and observation, is a flashing signpost pointing toward physics we haven't yet imagined. When JWST spotted those impossibly mature early galaxies, it didn't break cosmology. It handed us a wrench to dismantle and rebuild our models. When primordial gravitational waves play hide and seek in the cosmic microwave background, they're not taunting us, they're daring us to build better detectors. The most exhilarating part, right now as you watch this, thousands of scientists are chasing these mysteries with tools that would have seemed like magic a generation ago. Hyper-precise atomic clocks hunting for drifting fundamental constants, kilometer-scale gravitational wave detectors listening for spacetime's quantum hum. Space telescopes mapping dark matter's invisible web with gravitational lensing. This golden age of cosmology isn't about filling textbooks, it's about rewriting them in real time. So stay curious, that twinge of wonder you feel when confronted with these cosmic riddles. That's the same spark that drove Galileo to point his telescope at Jupiter's moons and Hubble to measure galaxies racing into the void. The universe isn't just stranger than we imagine. It's stranger than we can imagine, and that's what makes the search so beautiful. Whether we're decoding quantum imprints from the first trillionth of a second or debating the existence of bubble universes, every question reminds us we're not just observers of the cosmos. We're its conscious edge, reaching back through time to unravel the story of our own origins. The next chapter is being written right now, in supercomputer simulations, in underground detectors, in the mirrored eyes of giant telescopes scanning the night. And the most profound revelation of all might still be waiting, hidden in the next anomaly, the next paradox, the next cosmic whisper that says, "Look closer." Dig deeper, the best mysteries are yet to come.